as mutation testing. Sergej Dechand is going to explain to us what it is exactly. Sergej is CEO and co-founder of Code Intelligence from Bonn. He's an expert in usability aspects of IT security and has 10 years experience in software development, in software testing, IT security, and academic publishing. Before founding Code Intelligence with his colleagues in 2018, he worked as an external IT consultant and as a project manager at Fraunhofer FKIE, which is a top German knowledge institute with a specialty in communication, information processing, and ergonomics. So, very good cards to fill us in and make us smarter. Before I give the floor to Sergej, I would like to mention to you that you can ask your questions in the chat. I will present them to Sergej at the end of the talk or in between when it's very urgent. Sergej, you're on.
Yeah, thank you for the nice introduction, Garrett. So today I'm going to talk about doing fuzzing from the developer's perspective. And the goal is, because everyone is talking about shift left testing, and with fuzzing, you can push it even more shift left than you would expect to. So just a few words about me. So Garrett already did that a lot, but anyway, just to make it short, my background is usable security and privacy and secure code development. And I was teaching a lot code security best practices to students, but also to companies. And when I founded Code Intelligence with my other co-founders, basically, I got the responsibility being the bridge between the salespeople and the technical people. And a few words about Code Intelligence. We are a spin-off of the research group for usable security of the University of Bonn. And basically, our goal is to enable developers to protect against the unexpected, and fuzz testing is one of the best approaches here. But just a little background. So you probably heard about fuzz testing, and the word fuzz means to make or become blurred. So if we think about software development and fuzzing, basically it all started in the end of the 80s in an American university. And the goal there was basically that we have a fuzzing engine which produces random inputs, and those could be bytes or some specific numbers, and is given as an input to a system under test. And as soon as you find an input where your application crashes, you basically found a bug, had to fix the bug, and then start all over again. And this works quite well for very simple programs. But let's say we want to test an image parser, basically something like a JPEG parser, which is more complex. And if we just produce random data, we cover a lot of error code. But how likely is it to produce a valid JPEG image just by randomness? So very unlikely. And a lot of the code where a lot of bugs might be happening are somewhere deeply hidden, and you need to provide either valid JPEGs or something which is very similar to a valid JPEG for that. And so there are some limitations if you just do random testing. But fortunately, we also have data from unit tests. So fuzz testing evolved a bit and is not just random testing anymore. But let's say you have some data in your unit tests or system tests, and you want to combine it with randomness. So basically, you get a lot of data, what you already have as test inputs. You also add some randomness to that, and you also might add mutations. So basically, not only producing random byte streams and testing the static data, but you could mutate the data from the unit tests. Basically, you just flip a few bits and bytes inside that JPEG, and then you get something which is very similar to a real JPEG, but in the mutation, you somehow destroyed the header, and now it's an invalid JPEG, which cannot be shown, and you give that as an input to the image parser. And sometimes you create mutations which are valid JPEGs. You just switched the direction, how you produce the image, or you break it again, or you change the color. So there might be a lot of random stuff, random mutations going on in there. And the goal is basically to find a lot of states and crashes in the application. Again, if you found a crash, you want to fix it. Now we want to even improve that. So somehow here we only are able to find crashes, and we have to provide some sample data. But could we improve it even more? And here is where whitebox fuzzing, instrumented fuzzing comes in. So basically, we still want to test the same program, the JPEG parser as an example before, but now the magic happens with the so-called instrumentation. You can imagine it. So when compiling the program to the binary or to the bytecode, additionally to the program which is executed, you inject some markers into the code. And those markers are there to kind of give the fuzzing engine some feedback, what's going on inside the program. So what kind of branch have you covered? What kind of magic bytes are happening there? If you compare something, so basically you want to give as much feedback as possible. So now the goal is we don't want to give valid data because we don't know that we are testing a JPEG parser, and we start with just the byte 0 in the beginning. So it's basically an invalid image which is given to the application. But now when we give it as an input, what's basically happening, and we can observe it during runtime because of the instrumentation, is basically that you see what's happening inside the program. And here is a code sample from Commons Imaging, a very common library for handling the different image formats. And there, every file format has a specific constant. So something like every GIF starts with the bytes 4749, or every JPEG starts with FFP8. And this way, the image parser knows that now it has to handle a GIF image or a JPEG image. And what's happened then is that you go through all the constants, and basically you compare the first byte pairs. And then based on the byte pairs, you know what kind of image format has been produced, or what kind of image format you have to parse further. And what you see here, because we gave 0 as an input, is that you compare it with 4749, FFP8, and because none of the conditions is true, basically you are in the else branch that you have an unknown file format. And as I said, we gave it as a feedback to an AI algorithm within the fuzzing engine. And there you could do some predictions, because we have seen now that you are in a specific else branch, and we have also seen that the input is compared with FFD8. So maybe FFD8 is something what is important. So you basically produce, additionally to the random inputs, you could produce something starting with FFD8. And there you would see from the feedback of the program, basically, that now you reach a new path because now you are in a different branch. Again, you give it as an input, you give it back to the fuzzing engine, that now you reached a new valid state. And basically, again, you can make the decision, will you mutate the FFD8? Will you add something? You get new feedback. And then, without knowing that we are testing a JPEG parser right now, the fuzzing engine would produce a valid JPEG image which might look something like that. So it probably doesn't make sense for us just to create something with the color green. You could do further mutations there, and it could look like that or that. And you could also learn from unit test data, because if you run the unit test or system test data here, you would see whether it triggers some specific new paths and basically learn. And what's happening during fuzzing is basically what you see on the left. So you have a lot of up to thousands of executions per second. And while you are running it, you obviously don't want just to find the crashes inside the application. Obviously, you can use some specific algorithms, bug detections, security, vulnerability detection, and so on to know whether a bug is happening. So just to summarize the difference, how Blackbox fuzzing started basically in the end of 80s and was done until 2015 is basically that you generate some kind of inputs, you have some sample data, you could write some specific grammars that if you produce random data, it needs to be a specific range. And then this way you can reach or some specific code coverage. But because you are doing black box testing here, you don't really know without feedback what's happening inside the application. So this way you don't have an information what code is reached, and this way you can miss a lot of critical bugs. If we now are talking about coverage guided fuzzing, whitebox fuzzing, here we use intelligent algorithms, how to use the feedback, what's happening inside the program. So basically for the application, it looks like a maze, and you want to find all the different paths inside that maze to collect all the vulnerabilities and software bugs. So basically, fuzzing itself is something how you want to maximize the code coverage in an efficient way. And the detection algorithms are there to find whether some bugs or security issues are happening. And yeah, what's all the fuzz about? I mean, from 2015, fuzzing got a kind of renaissance that more and more people started to use it again, even though it was born in the late 80s, and it was the trick with the instrumentation. And one of the most prominent examples where fuzz testing produces super good results is the Google Chrome browser. So in the last 2.5 years, they found over 30,000 bugs automatically. And I think about 1/5 of those bugs was security critical. So not just crashes, you could find something like remote code execution and so on. And the Linux kernel and in the open source community, fuzz testing is pushing forward. And there are thousands of tutorials how you could find heartbleed within a second if you are using fuzzing. So there were denial of service attacks on one of the most famous blockchains. And even if you kind of don't have the source code, there are tricks how to do coverage-based fuzzing. And there was a tutorial for 50 CVEs in 50 days with the Adobe Reader. But what everything has in common is that mostly fuzzing was used for C and C++ applications, because there it's very easy to shoot yourself in the foot, and you want to protect against all the different kinds of things you can do wrong with C and C++. So all the buffer overflows, which can eventually lead to remote code execution. But now I guess a lot of people or a lot of people in the audience don't even use C and C++ and might think, okay, it doesn't concern me. I'm using a memory safe language. I'm using Go. I'm using something like Java. There are no buffer overflows. But again, should you fuzz it? Of course, because there are a lot of functional bugs. So you could produce a lot of exceptions which are not caught in the end, and then the user gets some weird error messages. You might have assertions inside your code, and fuzz testing is a good way to basically find inputs breaking your assertions. And you could think even further for the functional testing. If you have two different implementations of the same algorithm, you could make a comparison whether there are differences between them. So basically, you would expect that they produce the same in and outputs, and with differential fuzzing, you could basically compare the two different implementations, whether they give the same output for the same input. But what is even more important today is the security issues. Even in programming languages like in Java, you might create something like infinite loops or out of memory errors because you allocate too much memory and then your entire web backend crashes. And speaking of web backends, there are even more issues or even more things which can go wrong. I just say OWASP top 10, where you have SQL injections, cross-site scripting, something like remote code executions in specific ways. So even if you are using memory-safe languages, very bad things can happen, and fuzz testing would protect against it. So is fuzzing a case for shift-left testing? So with fuzz testing, a lot of inputs are generated automatically. So this is something what you can run inside a pipeline. And you don't have to maintain golden data because you can learn based on the instrumentation what kind of different inputs lead to different states. And this way you know more and more about the application. With dynamic testing, in comparison to static testing, you don't have any false positives because every time you give something as an input and with the output you get a broken assertion or you get something like a crash, you have the proof that something is happening. So this way, it's not something like you get a warning, there might be a SQL injection and you wonder really what is it, if it's sanitized here or there. With a dynamic approach, you always have the proof with this specific input, you break this, and you can even load it into your debugger and understand why this is happening. And it's highly parallelizable. I mean, because fuzz testing gets some feedback from the application. You can start several instances with several CPUs, and this way you basically can achieve a lot of throughput and can scale it up and down to your needs. And since we are not using Blackbox fuzzing and but compile time fuzzing, so as an attacker, if I'm attacking your application, I usually don't have the source code. And if I have the source code and I do compile time instrumentation, I kind of have, from my fuzzing perspective, always an edge over attackers because I have more information and this way can find more bugs compared to the attacker. And we as Code Intelligence, we open sourced a coverage guided Java fuzzer, which is available here on GitHub. And this is a very powerful fuzzer which uses the same algorithms to produce the different inputs as been done with C and C++. But what we do differently is the bug detection side. And basically, we have an agent. So basically, if you have an application, a running jar file, you can load that Java agent. And from there on, we would instrument the source code. And based on the instrumentation, we can do a kind of white box testing. And how would you do the fuzzing with, the open source application is Jazzer, basically a Java fuzzer. What you can do is something what is very similar to what you know from unit tests. In unit tests, you usually start with some specific inputs. You give that input to the application. Then the application gives you some specific output. And what you basically do is if I give input X to the application, it should reply with Y. In fuzz testing, it's a little bit different. So in fuzz testing, you are creating a fuzzer test1 input function. This specific function is there to basically get the data from the intelligent generator algorithm. And what you basically get as a parameter is the random or systematically mutated data. And in that case, it might be an array of bytes. And you just take those bytes and can test an application. And here we are testing commons compress. So there are a lot of compress algorithms. And what you would create is with new tar file, you are expecting a byte stream and you get that byte stream as an input. And you what would basically happen during fuzzing is that in an infinite loop, you would create more and generate a lot of different data. You would open the tar file, try to parse it, and then run it again. It's just 5 lines of code with what you could add. And what we found there is, for instance, an infinite loop. So if you are using in Java something what expects compressed data, we could produce inputs basically crashing your application. So for this, we register the CVE, and this just shows you with how little effort you can write new tests for that, testing your APIs. And people are really bad in writing parsers, handling the different network or file formats, because this is very hard to think about all the edge cases. And in this case, we find everything which is not just producing an IO exception. But this was a very simple example. What if you have a very complex application? So let's say you want to test an application which is doing some kind of base 64 encoding and some insecure encrypting. So basically, we have a function doing insecure encrypt, taking a long number as an input. And what it does is basically the static key inside the application is stored with the input the function gets. And the interface we want to test is basically this consume. This consume probably doesn't get just one input, but 3 inputs at once. So basically, it gets a string and 2 long parameters. And your application and the bug is hidden somewhere deep inside the code. So basically, to get to this line 19 here, you have to crack a lot of checks by the fuzzing. And I think that this example shows the capabilities, how fast it or how potential. So basically, it gives you a good feeling on what fuzzing can achieve. So basically, we get a string as an input, and only if the string contains jazzer as an input. And then we get another long input, which is in bytes, basically value. So basically, we are expecting the bytecodes representing the ASCII of value. And we are waiting for another input, which represents the word profile. And basically, we can trigger that bug only if the fuzzer produced with the string jazzer value profile. Only then we are triggering that bug. And if we would load that application again here, we want to make a fuzz test. So basically, we define a random class having the public static void function fuzzer test1 input. And instead of generating byte streams, we would create a fuzz data provider. And the fuzz data provider is basically a little library which can help you to take more than a single input from the fuzzer. So basically what we get is we consume a string with a length of up to 100. We consume 2 long numbers, and we give it to the consume function, which I just have shown. You get a string and 2 long numbers representing other strings. And if you get that, you need to basically return, and you need to, because we are using insecure encrypt here, so basically the number, or you get the value, put it into insecure encrypt, and then you get the other number out of there. And we are testing that. And it just takes you 5 seconds to get into that specific branch. And this is a good example to show that even complex workflow or even complex data flows would be cracked with fuzz testing. And Garrett, are there any questions so far? Okay, I guess there are no questions so far. And so those were very simple examples to find infinite loops, something like specific bugs. But we also found a few CVEs when we open sourced our application and tested it with open source solutions. So for instance, there is a GitHub project called JSON Sanitizer, and it's there that every time you are given a JSON-like content, the JSON Sanitizer converts it to a valid JSON. So the output is well-formed JSON, and it's not allowed to contain anything like a script so that you could do injections. And I got something in the chat. Yeah, so basically, now, what is usually happening, or where is the JSON Sanitizer used? So basically, you have a script in your HTML. You are expecting that you will load some specific JSON input. So something like you have here, foo, bar, and whatever you put into that JSON. And then you do some specific things with the config. For some reason. So, and we want to test that application because we know that now we are not allowed to have something like an end script tag, because as soon as we have something like end script, the HTML parser would probably end this a script, and you could inject something else. And what we basically get is a random input, put it into JSON Sanitizer sanitized, and we write an assertion telling basically that the output should never have this specific string, because otherwise you would be able to do an injection. And basically what the fuzzer then at some point produced is that it produced a script having this B script, whatever alert. This is then giving to the JSON Sanitizer. And what's happening here is that you are loading this specific config, and then you are ending the script, and then you inject an alert in there. And this way you are able to execute the code. And basically it was a valid bypass of the sanitizer to avoid XSS. And here we registered a CVE just showing the capabilities on that you are able to find much more than just infinite loops or some specific hashes inside the application. Yeah, and after open sourcing our Jazzer, the Java fuzzer, we started to collaborate on with Google on that. So basically, there is an initiative for fuzzing from Google. So if you have an open source project which is written in C, C++, and now also with Java, you are able to fuzz your application continuously inside the infrastructure with Google. So they give a lot of different thousands of CPUs for that, so that you can do it effectively. And there are already more than 450 different open source projects on board it. So something like curl, FFmpeg, Git, Kubernetes, and so on. And if you are onboarding your projects, you get a bounty for that up to 20,000 so 20K dollars for the onboarding. And we are collaborating with Google to enable Java fuzzing. Garrett, do you want to say something?
Yeah, there's a question might be useful to ask this at this moment. The question is, how long did it take to find the out-of-memory error in the example you gave, and what input triggered the error?
Do I have it here?
So it's a couple of sheets back.
Yeah. So if you go on the on GitHub for Jazzer, there is an example for that. You can run it yourself. I don't remember what the input was, but it was a very short input, and it took the fuzzer something like 2 or 3 seconds. It's happening very fast. You can run it yourself.
Okay, thank you.
So that was the only question, right?
Is another question, but I think I will save it to the end.
Okay, sure. Okay, but now I have shown some kind of API testing. So you are testing something like parsers and so on. But if we want to go beyond the library, so real world applications are much more complex. And I mean, the most used application form is our web applications. So usually you have some kind of web APIs running over HTTP, and then there you encapsulate JSON. So you have REST interfaces, maybe GraphQL or something like so. So it's a very complex application having different kinds of layers. So, and it might consist of many components. So you might have some different microservices, and it could run in complex deployments. So you might be running it inside Kubernetes, and you could use something like gRPC, REST, GraphQL, and so on. And you could even mix different programming languages like C, C++, Java, Go, and Python. So far, we have seen very simple examples to fuzz simple data. And the question is now, can fuzzing live up to the challenge to combine all the different real-world scenarios to do a kind of system-like fuzzing? And this is actually something where what we are working on with Code Intelligence, and are offering a solution for that. So basically, imagine you have a client. The client communicates over REST with a service. This service is written in Python. And then this service, depending on what the inputs are, is communicating over REST with another service, which might be written in Java. And over gRPC, it could communicate something with another service 3, which is written in Go. So basically, what we have to offer, or what we are offering, is that you are able to instrument the code automatically, even though it's deployed somewhere inside Docker or Kubernetes. And you can collect all the coverage from the single microservices in the fuzzer and give all the feedback. And with that, we collect the coverage information, all the dynamic states, what is happening there, and get some kind of error reporting. And what is basically happening there. So imagine that you have some kind of smart fuzzing for web applications. So if we now imagine we are scanning something like a Spring Boot application, and inside that Spring Boot, we have instrumented HTTP stack, JSON parser, validators. And now, instead of getting the binary fuzzing input like we have seen before, we expect some kind of structured format. And in that structured format, we might expect something like headers, where you have some kind of content types. You would have a body, which then could encapsulate something else, and so on. But the good thing about the coverage-based approach with the instrumentation is, so imagine you have a JSON parser, and the JSON parser is searching for some kind of fields like body we will see that it searches for those kind of keys. And this way, the fuzzer, based on the feedback it gets, could produce all that data. And this way, we can achieve more and more coverage. And this over the different services, because from the fuzzing perspective, each service is a kind of specific path inside the control flow, and you can combine all the things together and get a single input. And the end goal in the end is basically that with CI Fuzz, we want to integrate all the things inside a continuous integration. So we want to fuzz entire web deployments inside your continuous integration. So basically, as you can see on the right, you are writing a merge request, and the merge request then adds some new kind of code. And then imagine as a developer, you get a feedback that the deployment you just deployed found a SQL injection based here, and you could have a look on that. And basically, if you then click on view finding, you can have a look onto that. And this way you could even see in what kind of file with what kind of input you are triggering it. And here you see a sample from web code. And in web code, there is, for instance, the challenge 5, where you have to find the SQL injection. And what you see basically there is with the username login Larry, you are triggering some specific kind of condition, which leads to a SQL injection. And yeah, the goal from the developer's perspective would be that we have a fuzzing application which fuzzes every deployment I produce inside the merge request, and this way I get an instant feedback as soon as possible. And just a few takeaways here. So what we have seen is that if you use fuzzing correctly, you might have different kind of integrations, and it can happen at every development stage. So in case you have something like that you would test every single commit, you could even add it on pull requests, you can add it inside the nightlies. We have seen that it can be done on unit level. So basically you are testing some specific parsers, but it could also happen on a kind of system level where you already deployed the application inside of Kubernetes. And what you basically are trading here is you have engineering time where you have to think about all the cases you produce and review all the code, and you trade it for CPU time. And it not only makes sense to use it inside of memory unsafe languages like C and C++, we have found already various CVEs in open source for memory safe languages, because still very bad things like OWASP top 10 and all the kind of denial of service can happen. And if you produce an application and you are in possession of the source code, you can leverage the source code and have an edge against the attacker. So the main takeaway is probably that you shouldn't release bugs that can be found with fuzzing. Yeah, and with that, I'm open for questions.
Okay, thanks a lot. As promised, I've saved a question till the end. The question is that obviously 100% guarantee on bug-free software is not possible. But could you make strong quality claims after fuzz testing about code other than, well, the outcome? We can say that specific tests succeeded in the test circumstances.
Yeah, so with fuzz testing, it's kind of like with a pen test. You cannot make guarantees. So we often are compared against pen testers. And what we see a lot is that, so if there is a pen test running, we were running our software at the same time. And what we found there is that 80% of the bugs a pen tester produced with all the workflows, what are used with Blackbox fuzzing and whatever the pen tester is using, we also found with our approach, but automatically and inside the continuous development pipeline. But on top of that, we found a lot of issues which have been overseen by penetration testers, because many so-called enterprise penetration tests, they just do black box fuzzing with a little input from the penetration tester. And what is almost never done in practice is measuring the code coverage. And what we have seen a lot in the practice is that there were some kind of specific inputs where you could reach more paths which have not been tested by the pen tester, because the pen tester didn't even get access to the source code. And now imagine comparing the pen tester against an attacker. So if the attacker just does one thing better than the pen tester, obviously the attacker is in there, and the attacker just has to find one way. And with Whitebox fuzz testing, you kind of get a feeling what's happening. You get the coverage reports. You can have a look on what kind of lines of code have been covered, what kind of interfaces have been overlooked, so you can see it. And you would find much more edge cases. Would it protect against everything? No, of course not. Especially something is what you cannot decide during fuzzing automatically is, if I trigger a specific function, am I or can I do it without admin's rights or not? So this is something what a fuzzer cannot decide. So there is still someone who has to produce some kind of ruling for the fuzzer when the fuzzer should cry for error.
Okay, so 100% guarantee still not can be given, but a very strong claim, or much stronger claim, well, is I think possible now. Got another question. The difference between open source and the commercial alternatives. Can you tell something about that?
Yeah, so with the open source solutions, those are focusing a lot on API fuzzing within your API. So basically testing internal APIs. What is not open sourced yet is testing something like web APIs, because there the fuzzing is much more complicated, because you go over a lot of layers. And what you want to avoid is that the fuzz testing always basically improves the results of maximizing the code coverage of the JSON parser. But probably you are not testing your own JSON parser, you test the application behind REST and the JSON parsers. And so this is something what we offer with our commercial solution. And obviously all the integrations into the daily tooling. So integration into GitHub, GitLab, Jenkins pipelines, whatever is used in business.
Okay. Thanks. I will take a look at the chat if there are any further questions. Well, I think those were the questions. That leads me to a very big thank you very much for your contribution. I think it was very interesting. And I think you also will be happy to, if the attendees or the people listening have questions later on, to contact you directly. Yeah. So, okay.
Thank you.